probably answered. Let's stop now and see the word cloud of how it's going. Reveal counts. Word cloud. Good. Oh, yeah, that's good. Weather. I like that. Yeah. Okay. Pretty cooked. All right. This might be the summary. Well, okay. So yeah. So as you know, a lot of people are working hard on their tic-tac-toes. Remember, the tic-tac-toe is sort of a warm-up for the final. So even if you don't fully get it working as much as you want to, like, just do your best, and whatever you have, it will help you do the final. Last year, I made the final was like more unrelated to the assignments, and then people had a hard time. So you guys are having the hard time now rather than right before the final. So hopefully you'll learn something and you'll have a nice final. Okay. Any questions or comments before we get started? All right. Today we're going to finish up what we started last time, which is this vectorization idea. So we were vectorizing things, and so we were doing tic-tac-toe. And we said you can vectorize. We had the V my AI. V stands for vectorized. My AI inputs one board and calculates the best one. So my AI was up here. It inputs the moves. It calculates the value of each of the moves, and then it tells you which move had the highest value. So it's sort of doing a greedy AI. If you were going to put this in your code, you would have to either put the epsilon in here somewhere or put the epsilon in where you're getting it used, so to make sure you have some exploring. But that was my AI. Probably a lot of you guys have something similar to that. So the new thing was the vectored my AI, where we use this vmap function, JAX.vmap. And what that does is it lets you feed in not just one game at a time, but you can do like 1,000 games in parallel at a time. And the example we gave over here was we fed it in 2 boards, and it thinks on board 0 you should play move 6, and on board 1 you should play move 4. So that was the VMyAI on these 2 boards that we did over here. So that was from last class. And in a second I'm going to we're going to copy and paste the whole tic-tac-toe like game loop, how the actual games play, to make it work with multiple games at once. So that'll help you guys out for the final project and project or assignment 5. But any questions or comments about where we are so far with the VMap? JAX.vmap? Okay. So let's do that. So I'm going to take, this is the tic-tac-toe game loop for one game at a time. We're going to copy and paste it and make a tic-tac-toe for several games at a time. So, and you'll see what changes, and that will speed things up a huge amount. So this is like kind of bookkeeping. We're going to simulate many games at a time. Many. Okay, and then once again, I'm going to leave num episodes is like how many times we loop through it. So we're going to play however many games in parallel, like 1,000 games in parallel. Let's call that n batch. That's what people call it. So like, let's make that 100, and so we'll do 100 games in once at a time. Verbose, as usual, just whether or not you print it out. And now the AIs, they have to be vmapped. So we can do the VMyAI. The VMyAI. It doesn't have to be in all caps. So they have to be AIs that input multiple games at once, just like we did. So there you go. I'm gonna play myself. There's also there's a vectored version of the random move AI that will be provided to you as well. Then this part of the loop is the same for episodes and non-episodes. We're gonna run it some number of times. Where it starts to get different is over here. So in what you guys are used to, current player is a number. It's either 1 or 2 if it's player 1's turn or player 2's turn. Can anyone guess what it will be now? What will, instead of one single number for current player, what are we going to replace it with? Yeah.
Like a vector of players.
Exactly. Yes. So it will be a big vector of different things. So how do I make it a vector? Well, jax.random.uniform, right now I only fed in a random key, so it's outputting a number. But if I say do comma, and then I think I have to do it like this, n batch, comma, or I think you can even write like size equals n batch comma. Then it's going to make a vector of numbers. Let me run this code on its own and make sure it's working the way I think it's working. This is another good one. ChatGPT is fantastic for these like very simple things. If you feed it like one line, you're like, I'm trying to do this thing. I think it works like this. Am I wrong? And it will tell you. I probably have to run everything. Run straight. Yes, okay. Yes, you don't know what JAX is. Okay, rerun everything. Okay, now it's going to complain it doesn't know what n batch is, so let's make. What are we stuck on over here? Do we have something long? Okay. Okay, so current player is now a vector with two things in it. Of course, you might point out that in tic-tac-toe, it always alternates. So it goes like player one, player two, player one, player two, player one, player two. Why do I need an array to keep track of whose player it is on every single board? It's going to be the same player on all of them. Anyone want to guess why I'm doing a big vector? Yeah.
Because the games are going to be different lengths, they're going to like swap back and forth at different times.
Well, in tic-tac-toe, I think it would actually be fine because they always swap back. It goes 1, 2, 1, 2. You're right. I guess if a game ends, it keeps going 1, 2, 1, 2. But like if we program in our game logic that if the game is over, then just stop, then it'll be okay. It's actually in preparation for something else. Yeah.
Is it for like broadcasting or something?
No, it's not. You're thinking. You guys are making. You're thinking. There's a technical reason. There's a outside the world of the computer reason. Yeah.
Is it if you can roll it again? Can you use it to roll it again?
That's what it is. So in tic-tac-toe, of course, it doesn't matter. It always goes 1, 2, 1, 2, 1, 2. But in your final project, pig-tac-toe, the game's changed, right? So if you roll again or not, you can get another turn. You can get like 3 turns in a row if you're lucky. And so even though for tic-tac-toe, I could have done it with just one player, for your final project, it is a vector. We got to make it a vector so that we can have all the turns go at the same time. So that's why it has to be a vector. Okay, let's go back to this. So that is a vector. And you'll see a lot of what we have to do here is all the things that would happen only one at a time, they get replaced with vectors. So there's the first one is current player. The next one is board. Board before was an array of shape 3 by 3, and now it is going to be shape n batch by 3 by 3. N batch by 3 by 3. There's a very common convention that you put the batch size as the 0th entry. And so this is a good warning for you when you go to upgrade your code for the final project. If you have anything like axis equals 1 and axis equals 2 in your code, you will have to change those. So a very common convention is to use things like axis equals -1, axis equals -2, which is saying go start from the end. So axis equals -1 would be going over the columns, axis equals -2 is going over the rows. And if you have the batch dimension or not, it still works both ways. So if you have some code with 1s and 2s, you might want to replace them with -1s and -2s. Okay, here's another one. Game over equals false. If you're playing one game at a time, the game is either still going or not. If you're playing 100 games at once, this is going to be a vector, and that's going to be zeros. So I made it all zeros, and then I said make them booleans, so make them trues and falses. So there we go. Okay. There's some, okay, you gotta also worry about the random keys. I'm not gonna worry too much about that for now. I think in the final version of the code that I gave to you guys, the keys are also taken care of, and they are split amongst the games, but for now, let's just, let's leave that. So game over and current player, those are the things that have to get done. This is the first place where things are gonna kind of get a little funky. In the one player game, you're like, look, you just go until the game is over. Of course, you have many games. You can't just say, is one game over? You want all the games to be over. So if jnp.any of the game overs are true, wait, I guess I want all. If all the games are over, so I want not this. So all games over equals false. Okay, yeah, that's what I want. Okay, all I needed to do is that I bamboozled myself with the nots. Okay, if all the games are over, then we will stop. Otherwise, we keep going. And so this jnp.all, it makes sure that it checks every single entry in the way we said before. Okay. Here's the nice thing, moves in legal, that works exactly the same as before. So this possible moves function, which I wrote, was set up so that it uses ... dots, and it will automatically work. So board is all the games, and so it has shape n batch by 3 by 3, and it will return n batch by 9 by 3 by 3 for the moves, and n batch by 9 for the legal. So these will now be arrays, not things. If you want it to be pedantic, you could add an S everywhere. So they could be like boards, legals, moveses, but we'll just call them the same thing. Okay, and here is where things get even more spicy. We want to avoid if statements. We can't just do if current player equals 1, current player equals 2. The way you do if statements is you do jnp.where. So we're going to do a jnp.where, and we're going to do where the current player is equal to 1. Then we will set the move index to where the first player would play. So player 1's move, and otherwise it'll be player 2's move. Player 2's move, like that. If Google cut me off. Okay, so that's what that's gonna replace these if statements, and then we're gonna have to calculate the moves for player 1 and 2. One thing that is a little bit annoying is when you do JNP.where, you actually have to calculate both of these things. So you have to calculate both player 1 and 2's move. What would player 1 do in this situation? What would player 2 do in this situation? And then we just like, if it's player 1's turn, then player 1 gets the choice, right? Like, so we're going to calculate both, and then we're only going to like pick out the right one. Question over here.
Can you explain why it's JNP all at the same?
Oh yes, okay, this is great. So yeah, maybe I do have it wrong. So what I would like it to do, let me say what I would like it to do in words, and then we'll figure out if what I wrote down actually does what I want it to do. If any individual game is still going on, we got to keep going. If all the games are over, then we can stop. So if all of the games are over, then this will be true. So game over is a vector. Is the first game going? Is the second game going? Is the third game going? JNP.all of game over says, is every single one true? That would mean every single game is over. If every single game is over, then we wouldn't do all this stuff. But if not, if it's false, then we gotta keep going. You'll see this in a second, that we're gonna have to write in some code that says if the game is over, don't do anything. So you'll see that come up again. But yeah, maybe I got it wrong. I think it's correct. Does anyone want to weigh in? It's good? Yeah?
Sorry, did you say that you want all the games to be over?
I want it to exit the loop if all the games are over, and I want it to not exit the loop if there's even a single game still going on. Maybe, okay, you know what? Actually, regardless, if we're having trouble reading it now, then when we come back in an hour after things are weird, it's going to be even harder. So let's do it this way. Let's put it at the end of the loop, and we'll say, if all the games are over, then break. So this is a little bit easier to read. We don't have a not, right? Even the wisest of Boolean people will get confused by a not, let alone us. So we gotta make it easier to read. Okay, so this is a good fix. Unfortunately, now it's going to yell at me about indentation. So let's see if I can remember the shortcut to unindent. Shift question mark? Nope. Command shift question mark? Nope. Shift tab, someone saying? Shift tab. Yeah, shift tab works. Okay. Very nice. Thank you. Okay. All right, where were we? Okay, so turns. So yeah, so it's important. Possible moves is already set up to work with this. We got to calculate both of these players' moves. So we're going to do this now. So player 1's move is something, and player 2's move is something else. And we're basically going to copy and paste. So what would happen? It's these things. So this is what player 1 would do. And this is what player 2 would do. Okay, and it has the swapsies built into it already, so that you can always pretend, when you're an AI, you can always pretend that you're player 1, because what we do is we always swap the board. If you were actually player 2, before we ask the AI what it would like to do, we swap it so that it looks like it's player 1's turn. Player 1 is always the active player from the point of view of the AI. So there we go. We calculated both player 1 and player 2, and then we used the JNP.where as a sort of an if statement to pull out the right move. And once again, player 1's move and player 2's move, they're big arrays, right? It's not just one number, it's like multiple numbers. What would you do on all of these boards? And that's because the AIs are things that input a batch of boards at once. All right. Okay, players 1 move, player 2 move. Board equals select moves by index, moves, move index. Technically, you would have to rewrite this, right? Because move index before was a number, and moves was one array. Now moves has an extra big array with one extra dimension, and move index is itself an array. But fortunately, select move by index was written in a way that works quite nicely with ... so it's all fine. So there we go. Okay, this one, what will happen when you run this line? It will explode, because print board is expecting one board, not right now board is a whole bunch of things. So what you should do is you should make it say print board of 0. So that'll print out the 0th board. When you're writing these things, you can't look at like hundreds of them at once, so you just maybe look at one. Okay. All right. This line will still work. Any 3 in a line, that still works. Board equals current player will be have an extra dimension, but any 3 in a line still works. And now game over will be, instead of being just one number, is the game over yes or no? It'll be a big vector, so that is perfectly fine. Current player equals 3 minus current player, this still works as well. So everything is fine. We have done it. You know, it wasn't that bad. You just have to think in terms of vectors. There is one super duper important thing that I said I would do, and I never did. So actually, as written, it'll just go totally bonkers crazy, and you won't understand what it's doing at all, because you forgot to do the thing that I said we got to do. Anyone remember what what was the thing I said we got to do? Yeah. Deal with the keys. Yeah, don't worry about the keys. The keys are fine. The keys take care of themselves. It's not the keys. Yeah. So before we were playing the game until the game was over, and that was fine. But now we're playing the game until all of the games are over. So this adds something we gotta make sure to do. Otherwise things will not work. So we're gonna run this loop until, remember, we're running this loop until all the games are over, and then we stop. And we're gonna run it over and over and over again until all the games are over. Yeah? Yeah, this is the right idea. You need some kind of, so a while loop would check and see if the game is over, stop playing the game. And that is the idea that we need. So a while loop won't actually help us here, because sort of if any kind of loop would deal with all the games at the same time. So what we need to do is look at each individual game and actually put in some kind of mechanism that makes sure that if a game is over, even if the rest of the games are still simulating, right? So game 3 ended, X is 1, but the rest of the games are still going. We need to make sure that we don't mess with game 3. Game 3 needs to stay the way it is at the end of the game until all the other games are over, and then we'll stop. So you need to do something to stop the games that are over from still getting updated. And as written, this is just going to update all the games over and over and over again until every single game is done. So this would be like you're playing tic-tac-toe. You got like 3 people playing tic-tac-toe. I guess you have 100 people playing tic-tac-toe, and even if you lose your game, you get to keep playing until the person over there finishes their game, which is silly. So we got to add in something that makes sure that the boards don't change. And I think the easiest place is over here, where we update the board. So instead of updating all of the boards, let's only update the boards where the games are still playing. Any game where the game is over, do not update it. And as usual, to do an if statement, we're going to use the where command. So what we're going to do is jnp.where the game is not over. So how do I do the game is not over? I can do jnp.logical not of game over. Okay, so where the games are not over, then do this. If the game is over, what do we want to do? Okay. I broke my rule with the not, right? Because game over is a kind of not. So why don't we write it like this? If the game is over, then do nothing. And then if the game is not over, then we will update the game. And what does do nothing mean? It means just leave it alone. So the board gets left alone. If the game is over, then the board is the board. Didn't change it. If the game is not over, then we select the moves that were chosen. Okay, and it doesn't like my bracket for a reason. Yeah?
Wouldn't that also mean that where the game is over, select moves, the board automatically is itself when it's... Oh, no.
Yeah, so one thing that is true that's like a little funny is this select move by index is going to get called even for the games that are over. It's just that we won't update the board for it. So remember before I said that we have all these like 100 people in a row, and I'm like, listen, your game's over, stop playing. Actually, what's going to happen is the person will get their marker out to try to play, and then by magic, when they write down the marker, it doesn't get recorded. So it's like I'm torturing these computers and making them play games and then not writing down their moves. Yeah, that's what's happening. Okay, so that's basically it, and this will work. And now what you have is we have lots and lots of games at once. You'll notice at the end, net victory points, all of these commands were set up with the ... They will still work just fine. Net victory points before was either +1 or 0 or -1. Now it is a big long vector of +1s, 0s, and -1s with who won the game. And what this lets you do is it lets you run many, many games in parallel. So instead of running one game at a time, you can now easily run thousands of games at a time, and it will still work. So you can make nbatch. I think you can make it like 100,000 before things start to get slow. So like you really can run tons and tons of simulations all at once in almost the same amount of time that it takes to run one simulation. So all of you guys who are struggling, you're like, I'm waiting for it to run. It took like 100, it took 1,000. It's taking so long. When we move on to the next assignment, you'll be able to do it a lot faster because the next assignment is very similar, but asking you to do things in parallel in preparation for the final. Okay, so that's it for parallelizing. So maybe what I'll do now is I will show you the code for the final project, which has all of this done for you.
I have a
Yeah.
So instead of using where, could you use like at set?
Oh, yeah, that's a good point. You could probably use at set.
That might be a little more efficient than.
Yes. Yeah, that's a good question. It would be interesting to see if you could do at set. Okay, I'll tell you why at set is annoying. At set is great if you're like, I know I need to update index number 7. So if we were going to use at set, we would first have to extract out of game over which of the indices have trues in them, which is actually kind of an annoying operation to do. So so you could do like at game over equals true, do this. So that extra operation, I think, will make it more efficient to do it this way. So np.where is actually super efficient. It does seem very silly from a human point of view, because you're a human, you're thinking of, if I have to do two things, you have to do one and the other. But actually on the computer, JAX is extremely smart, and it knows that if you do a np.where, it can calculate both of these two things at the same time. So what it does is it takes your computer, which has 8 cores in the CPU, and it says, cores number 0 to 4, please calculate board. Cores number 5 to 8, please calculate select moves by index. And then we'll smash them together with this thing as we were told to do. And so it takes about as long as the maximum of those two things to do. It doesn't actually take much more time than either of them individually, which seems like crazy, but that's the way these vectorized things work. Great question. Okay, any other questions before I flip over to the other thing? Okay, so let me show you the code for the final project, which also extremely similar. Pig Tac Toe. Okay, here it is. So this Pig Tac Toe thing, this is going to be the final project, and it is very, very, very similar to Tic Tac Toe. All the same commands as before. Create canal lines. All the stuff you've been doing, all the stuff you've been struggling with on this assignment will hopefully help you understand what's going on here. Possible moves, exactly the same as before. Legal moves, everything is exactly the same. P1, P2 stop, select moves by index, all of it identical. What is two small differences in the AIs? One is the AI, I made it input not only the moves that are available, but also what the current board is. So I know in tic-tac-toe, we ended up with this hack of taking the minimum to figure out what the board was. In pig-tac-toe, the AI also gets to see what the current board is, as well as the other things. That is actually super important, for example, when you figure out if you want to roll or not, right? You want to know, hey, if I rolled and I failed, what would happen? Where would we end up? So it's not enough to know just the available moves. You also want to know where we were coming from. So you're given this board, but of course that doesn't affect the random AI. The random AI just ignores all that information and picks randomly. And the only other thing is your roll again has to be included as part of your AI. So in tic-tac-toe, you just chose the move index. In pig-tac-toe, move index, and do you want to roll again or not? Okay. So there you go. Here's the simulation. This part is identical to tic-tac-toe, same printing function, same loops as before. Pig-tac-toe has a little bit of extra game logic. So if you actually read the code, you will see that there's this part where you have to, if they rolled again or not, if they chose to roll again, then something happens. If they didn't choose to roll again, then something else happens. So you should read that and understand how it works. It's not too difficult. It's implementing the logic of the idea of before. And the game only ends when there is no empty squares left on the board. So it doesn't end when the first person gets a 3 in a row. It ends when the whole board is full. And then the fun thing underneath here, so here's one game printed out, playing the two random AIs against themselves. But here is the batch version. And all of this stuff in comments has the VMAP version. So you can VMAP your own things. And then it has the multi-game thing here with n batch equals 1,000. And all of the things are implemented for you. So all of the game logic over here is written with these .where commands. So the move index, where the current player is 1, player 1's turn. Roll again, where player equals 1, do the roll again of 1 or 2. And then it does some stuff to do the rolls again in the same way. So it has these conditions, and then it's doing gmp.wheres to implement that if you chose to roll again or not, something will happen to you or not. It also uses array broadcasting to take the condition and broadcast it to the boards. All right, so that will be the final project. And it will also be, when you do assignment 5, which is the one after assignment 4, it is going to be like a baby version of the final project. For assignment 5, what you're going to do is you're going to make an AI that does exactly the final project, except its roll again is something very simple. Its roll again is always false. So your assignment 5 will be to do the final project, but because roll again is false, it's a lot simpler. You don't have to decide whether or not to roll again. You're making an AI that is very timid and always chooses to not roll again. It's actually pretty fun when you play against the random AI, because the random AI just like will go really hard and like have like 4 O's and still be rolling again. So it's sort of like you get one at a time, and you're going to be playing against the random AI who's like throwing down a lot, but occasionally like loses all of them. And you're going to have to run it. It's going to be just like your tic-tac-toe. You have to learn the basics, figure out how to do the parameters. You can either do Monte Carlo or TD learning, and you're going to try to make an AI that beats the random move AI. You should definitely learn to use the multiple at once, the batch learning, because otherwise tic-tac-toe, because it's a 4x4 board and it goes till the end, is sort of too big to do one game at a time. You got to learn how to do multiple games at a time. So that'll be assignment 5 and the final project. Questions or comments about that? Yeah.
When is assignment 5 coming out?
Yeah, so I told you what it is now. I will post it up like today. So all the code has been up for a while, and then you're gonna just play only against the random AI. Actually, the random AI, because you're handicapped, you can never choose to roll again. Playing against the random AI is like a good, like a worthy opponent. It's not like some loser who sucks. Like because the AI can roll again and you can't roll again, like if you can beat them about half the time, that's pretty good. Yeah, so that'll be posted, and yeah, you have all the code. You can start anytime. And it will be the final project, so the better you make your assignment 5, the more of a leg up you will have for your final project as well. Okay, so what are we going to do for the rest of the classes? So today we're going to show you some tricks on fancier value functions you can make. So far, the value functions we've made, you take the parameters, you add them all up. So you do the parameters for this thing, the parameters for that thing, you add them all up. We're going to show you fancier stuff you can do for your parameters. So I'm going to start by showing you in JAX, and then we're going to have a little tutorial on how to do it in something called Torch, which is also very common. Probably for this course, everything else is in JAX, so you might want to use JAX, but Torch is like a little bit more user-friendly, so you could consider doing that if you really wanted. Okay, so what did I want to show you? I want to show you this thing. So this is a very fancy value function that I've defined. How did I define it? It's over here. So here's what it looks like. And it's called F1. Let me draw a picture of what F1 is doing. Okay, so these are, I'm going to call these fancy value functions. Okay, and what do you guys have so far is, so far in, say, tic-tac-toe, you have the board, which is some array, and what you guys have done is you have converted the board into what I call features. So there's feature 1, feature 2, all the way down to feature. If you did it exactly the way I did it, you'll have 24 features. Feature 24, that's because there were 8 features for 3 different things. And then you combine these features into one single number. So you said, we've got one number over here, that's going to be the value, v of parameters, comma, board. And what did we do? We took the features and we multiplied them by numbers. So feature 1 got multiplied by theta 1. So we multiply it by whatever the first parameter is. And feature 2 got multiplied by theta 2, all the way up to feature 24. And then we had this big sum of taking our 24 features, multiplying them by 24 parameters, and you just add them together. So I guess maybe it goes without saying, there's a big plus over here. Let's draw the plus explicitly. So these get combined with a plus, and that value is the output. So this is a linear value function. It's a linear in the parameters, right? If you double one parameter, then however much it affects that feature will double. And like it was your job to come up with what are the features, what features are relevant to the game or not. That will help your AI sort of learn. But at the end of the day, you had these parameters. Okay, so that's what we have so far. We're going to make it fancy in a second. But questions or comments on where we are so far? Okay, so how do we make it fancy? fancy maybe is the wrong word. Maybe the right word is do it more. So imagine instead of 24 parameters, we had 48 parameters. We could just come up with some other number over here. So we could have, theta 1, 2. Theta 1, 2. So we have another set of 24 parameters. And instead of calculating the value function directly, we first calculate that number, then we calculate this number. So these are two different numbers. And then we can combine the two numbers with yet more parameters. So we have like theta 3, 1 and theta 3, 2. And those will combine to, so you take whatever the output is over here. So this is some output, right? This was the sum of theta I 2 times feature I. Feature I. And then we will multiply that by theta 3, 2, and we will combine it over here with a plus. So we take the outputs of what we had before, and we add more parameters, and we smoosh them together, and then we get even more stuff. So we get the value function over here via params. And so the final output, instead of being one sort of layer of doing this operation, is 2 layers of doing this operation. So that is a way you can put in even more parameters in your function. So this has some pros and cons. One pro, okay, let me tell you the cons first. Actually, you guys can probably guess. What are the cons? So this is like, yo dog, I heard you like parameters. So I put parameters in your parameters, and now there's a lot of parameters. Can anyone think of a reason this would be a dumb idea? Yeah. Yeah, it takes longer to learn. So I have just taken, you guys had nice 24 parameters. I've doubled them to 48, and then I added 2 more. So now we're up to 50 parameters. And so the more parameters you have, the longer you should expect it to learn. Especially if you're doing Monte Carlo learning, it's a very one-to-one thing. Like every time you run a simulation, you can learn a little bit. If you have 50 things to learn versus 20 things to learn versus 10 things to learn, it's going to take more simulations to figure it out. So potentially takes longer. Takes longer. So if you try to do these like giant, soups of parameters, and you're doing one game at a time, it will be quite slow. But if you're doing 10,000 games at a time, then you'll be okay. So it can take longer, but you got to fight it with efficient coding and bigger computers. What is the pro? Can anyone think of a pro of this thing? Yeah.
They probably fit better.
Yes. Okay. Well, so there's 2 things. You could imagine if you have more parameters, your function can be more flexible. So what kinds of functions could it represent? And you can go back to what we were doing with fitting points, right? So as a very crude example, we were saying when we first started learning about parameters, we said the classical thing is like imagine in 1D you have x and y values, and you want to fit some model to some points. So maybe you have 3 x points, x1, x2, x3. You have 3 y points, y1, y2, y3. And you would like to fit a function with parameters so that v of theta comma xi is approximately yi. Well, if your function is linear, like if you only do one layer, then the best you can do is something like this, right? That kind of is sacrificing. It doesn't go through any of them perfectly. It's just doing its best. It's a very simple function. If you start doing these like parameters of parameters of parameters, then you could imagine that perhaps the function we can do is more complicated. Maybe the function can kind of like scoop up everything. So here I drew it kind of badly. Maybe I want it like that. And I will say in the data science world and statistics world, there is such a thing as overfitting. You don't want to fit too much. But I will tell you that overfitting is a symptom of like not enough data. So you can if you don't have a lot of data, you can overfit. In what we're doing, you can always run more simulations. So you will never overfit as long as you can run it for longer and longer and longer. So maybe you need to run it for longer. It takes longer. But overfitting can always be overcome in our universe because we can just generate as much data as we need to overcome the overfitting. So don't worry about that if you've never heard about it or if you have heard about it. So you can imagine that this is better. It's more flexible. So more flexible. More flexible, question mark. And that's a very nice thought. Unfortunately, as I stated it over here, of adding these things and then taking the things you added and multiplying them again, really what I did was matrix multiplication. So going from the features to these two things, that is multiplication by a matrix of size 24 by 2. So this is actually matrix multiplication, and you could stack the thetas into these two columns. Theta 1, and then over here is theta 2, 1, all the way down to theta 2, 24. And what I'm doing is a matrix multiplication by this long, skinny matrix to get from 24 things down to 2 things. And then when I went from 2 things down to 1 thing, that was also matrix multiplication by 2 numbers. So theta 1 and theta 2, 3. So first I multiplied it by a skinny matrix, then I multiplied it by a very small matrix. And there's a property of matrix multiplication. If you first multiply by one matrix, and then you second multiply by another matrix, you might as well have multiplied by just one matrix, which was the product of the 2 matrices. So what I have done is a fancy version of doing what we had before. Before it was a linear function. Now it's still a linear function because it's still made of matrix multiplication. And the problem is, no matter how many layers you add on and how wide you make it, what I have described so far is always linear and will always be just a linear function. It will always just be matrix multiplication. So as described, it doesn't do anything. It takes longer. It's not even more flexible. You can still only do lines. But fortunately for us, there is one extremely simple thing you can do to break out of the world of linear things. And if you do that, then it really will be more flexible, and it will sort of unlock a miracle of 21st century technology and let us find, basically fit anything as long as we use enough parameters. Does anyone know what the simple thing to do to break free from the world of linear functions is? Yeah.
Add a step function to the output?
Yeah, you gotta add a step function somewhere. If you add it to the output, we'll be doing a linear function and doing a step function at the output. But the really clever place to do the step function is in the middle. So if you add a step function before you do this, you feed it through some little step, some nonlinear function over here. So before we do the last little layer, we're going to take our 2 intermediate values, and we're going to do some kind of step function to them. So something nonlinear. This is a nonlinear function. So once you do a nonlinear function, and you do it sort of in the middle of our computation, then it breaks us free of linear land. So even though the first layer was linear, as soon as we do this nonlinear stuff, then when we do the second layer, now the function that we're representing is extremely complicated and could be anything. Okay. So, and once you do that, we have discovered this is what a neural network is. A neural network. So people for a long time were working with these, starting in like the 50s, and they weren't working that well. And part of the reason was they weren't doing enough nonlinear stuff, and they weren't stacking enough layers. So if you stack a lot of layers with a neural network, and you use nonlinearities in between, you can make extremely, extremely specific functions that can fit almost anything. So the functions that you get are really good at fitting through everything, and they sort of do what you want them to do. So this is called a neural network. The one I drew for you on the board today is a fully connected neural network, and it also has a fancy name called a multi-layer perceptron. Multi-layer perceptron. Okay, and so this is one way you can take anything you did in tic-tac-toe, the hard part was coming up with these features. You'll be able to soup it up by just adding a lot of parameters, and as long as you're willing to take a lot longer of a simulation with more games, then you will still be able to learn. And the beautiful thing is that all of the hard work of figuring out what is the derivative here to do gradient descent is all still baked into JAX.grad. So if you were doing JAX.grad before, it will still work, and it will calculate everything for you. If you wanted to figure out the gradient by hand, it would be some complicated process of kind of working backwards. It's called backwards propagation. Fortunately, you don't need to know that. You just need to know this JAX.grad command. So I'm going to show you that in the code in 1 second. But this is like the theory sort of what we're doing. And these fancy value functions will help you make more flexible things that can learn more complicated patterns. All right. Any questions or comments? Yeah.
Is there what class of functions can it?
Yes, this is great. So it depends on what nonlinearity you use. One that people highly recommend is to use a piecewise linear nonlinearity called the ReLU function. So if you use the nonlinearity, which is this is called the ReLU function, which stands for rectified linear unit. But it's a very simple nonlinear function. So because this function is piecewise linear, so it's not linear, but it is made of two pieces, each of which are linear, the function you get at the end of your neural network will also be piecewise linear. And in fact, the number of pieces that it can be linear on is something like the number of parameters over here. So what you can think of is instead of having one green line over here, if you use 12 parameters like this, you're going to have 12 pieces of line that can be arranged. So maybe it'll be the blue curve that I drew is curvy, is kind of a fantasy. It'll actually be something like this. I don't know, but it will go through all the points. And you can play with it and see what it is. Typically, when people do these things, both the number of inputs and the number of outputs are huge. So like the number of inputs can be like in the thousands, and the number of outputs can also be like, for a good example is ChatGPT. ChatGPT has one output for every possible word in the English language. So it has like 10,000 possible outputs as well. And so you have these like piecewise linear functions on 10,000 dimensional spaces is some like crazy thing. But for us, fortunately, we're only ever working with the value function, so we're always doing one-dimensional outputs. And the number of features, the number of inputs is entirely up to you. So you can pick how complicated you want the board to be or not, and how many layers and things you want to do. Great question. Okay, any other questions? Okay, let's look at the code. Let me show you how the code works. So I want to go here. Okay, so here is my neural network. It's a function, just like before. It has x and the parameters, just like before. I guess were we doing it in the other order? Because when you do the gradient, by default it goes the other way. Okay, well I'm gonna leave it for now. Just be careful. So when you do, this is the reason I'm a little worried. When you do JAX.grad, we'll do, it does the derivative with respect to the first input.
Yeah, we had it the other way.
Do the derivative with respect to, I'll say the 0th input. So if you write it as f1x parameters and you try to do JAX.grad of this, that's probably not what you want. You probably want to do the derivative with respect to the parameters, so watch out for that. I think in this code it actually is okay, and that's because I never do the gradient of f directly. I do the gradient of the loss function. So as long as the loss function is defined with the parameters first, which I think it is, yeah, here's the loss. So the loss function only depends on theta, and then I do the gradient of the loss, and then I do f of x theta, so it's all fine. But do watch out for that. Of course, you can change the default. I think you can say like, this is a great question for ChatGPT. How do you change it to make it do the derivative with respect to the 1th input or the 2th input is totally fine. Okay, so that is one thing. Great, okay, so how does this network work? So I take the parameters, and the first thing I do is I unpackage them. So this network has 3 layers. The layers are called W1, B1, W2, B2, W3, and B3. Let me show you in a picture what these look like. So X is some vector. So here is X, some vector. Those are, in your programs, those will be the feature vectors, but it'll have like X1, X2, X3, X4, all the way up to Xn. And then I do a matrix multiplication with something called W1. And that is, like we were doing before, that's going to come up with some output, which will be, depending on the size of W1, will be the intermediate layer over here, W1. So let's pretend it's 3. And I add these up with a plus. That's just straight matrix multiplication. And as a vector, this is the vector you get over here is W1 times the vector x, right? So the dimensions of W have to match the dimensions of x on one side, and they have to match the dimensions of this 3 hidden layer on the other side. That is W1 times x. And then we're going to do something that I didn't mention before, but is also extremely helpful, which is we're just going to add on some numbers. So there's new parameters here, B1, 1, B1, 2, and B1, 3, and those get added on. So you do plus B1. And so that is a new vector of size 3, linear with respect to x, and then add on these b's. W usually stands for weight, and B stands for bias. Bias. Okay, and the biases let it like calibrate itself. If it wants it to be very positive or negative, it can do that. And now we do the nonlinear function. So now we feed all three of these through the nonlinear function, and that is applied over here at the end, like that, to get 3 values as output. And those 3 outputs, that'll be the next layer, and we're just going to repeat the process one more time, pretending these 3 outputs are the input as before. So let's see what this looks like in our code. So this is what I call the first hidden layer, and that first matrix multiplication is JNP dot of x with W1. That is doing the matrix multiplication, and it does it in a way that is nice with the if x has extra axes. And then I do plus B1, and then I apply the ReLU function that I told you about before. By the way, the ReLU function is, you can write it like this. It's the maximum of 0 and x. But that's the ReLU function. So that's the first hidden layer. And then we do it again. So if you were going to my picture, we would do it one more time. So we would take this whole thing, and we would do one more layer. Plus, plus, plus. And then more B's coming out the end. And then you would do more nonlinear stuff to get another hidden layer. So I'd call this thing the output over here. This is I called this hidden. I could have maybe called it hidden 1. And then the output over here, I call this hidden 2. And so that is some other thing. And then finally, you get the output. And the output, I did another hidden layer, but you'll notice I did not do a ReLU. So there was no nonlinearity at the end. And that's because I want the output to be both positive and negative. I don't want to exclude the positive functions. So that makes a function called f1. There's one other thing you need here, which is how do you start the parameters? And so I made a function called init_params that makes the parameters, and it makes them the sizes that you want. And that function is over here. It uses the JAX.random.normal to make the W1s and the B1s sort of at random. So they start at random, and they're all the right sizes to make all the matrix multiplications work correctly. And this is how it works. So if I run all this, what do I get to? I get my function f. OK. Question here? No. OK. Let's see. What is it doing? It's probably loading the package. Yeah, so this is the code we did before, where we had we were doing linear functions. We were trying to match those orange dots. And we were doing it with a gradient descent. OK, let's see. Why is it freaking out here? So here's my function f, and it is applied to all of the points that you gave it. So capital X is all the points. You might notice, if you were paying attention, f1 actually only inputs 1 point at a time. So even though I drew it in my diagram as having many things, f only inputs 1 point at a time. And to get the function that I wanted that can input multiple things, I vmapped it. So just like we talked about. So now my neural network, instead of just doing one example at a time, it can run many, many examples at a time, which is helpful. So that's my capital F, just like before. And then I have the same loss function as before. I input the parameters, and I do the loss. Here is the thing. Let's see what this is. If I do the grad loss of params, what is it? So before, when we were doing the gradient of the loss, it was one array. And that's why you could update them. But now you'll notice there's a curly bracket at the beginning. It is not one array. It is actually a tuple of arrays. And that's because there are 6 things in there. There is W1, B1, W2, B2, W3, B3. And all of those have to get updated. So the very simple-minded way to update, when you go over here, this is what's going wrong. You cannot add tuples like this. So what you have to do is you have to do something like this. For p-val, let's say in range, p-index, that's a better name. Thanks, Google. In range, len of params. Oh, beautiful. Thank you. Thank you, thank you, thank you. OK, so that's I'm going to do the update. So what this is doing is you can't just subtract 2 tuples. You have to get all the individual things. And I think Google did it right for me. That's not how I was going to do it. So I'm going to let's tell Google to get out of here. I guess this is in JAX. You've got to do it. OK, I'll show you a faster way to do this next class. So this is, nobody ever actually does this in real life because there's this other faster way that's much better that I'll show you later.